Hello everyone, welcome to mini lesson number 6. Today we're going to talk about related rates. That's section 4.1. I really want to talk about a problem that has a fixed variable in it, so a constant in it. But I'm going to start off with all related rates problems. Historically, these are the problems that my students have come back after the AP test and say, I forgot how to do a related rates problem. There was a related rates problem and my mind went blank. So I'm going over this. This is one of the mini lessons that I think are important because it comes up so often on the AP test. Well, what is a related rate? A related rate is a problem where all the variables, could be more than 2, could be 3 or 4 or 5, they're all changing with respect to time. So it's 2 different variables changing with another variable, t, which isn't even in the problem. They usually start with a formula, so you have to know basic formulas, things like the area of a triangle or the volume of a cube or things like that. On the AP test, they usually give you the formulas that you need. I want you to have some common sense and know what these formulas are. When you differentiate a related rates problem, every variable has a d something with it. If it's a v, it's going to be dv. If it's a rate, then it's a d something in the problem. Think of it like an implicit differentiation problem, but everything is implicit. If it's changing, you can't plug it in until after you differentiate. So if something is changing, if a variable is changing, it's getting longer or shorter or taller or whatever, you cannot plug it in until after you differentiate. However, this is what we're going to talk about today. If it's constant throughout the problem, you can plug it in at the beginning. That saves you a lot of time. Let's try this one. It's 3 problems, but they all go together. The length of a rectangle is decreasing at a rate of 2 centimeters per second, while the width is increasing at a rate of 2 centimeters per second. So, L is not 2. It's changing. So, dl is equal to 2. And even that's not right. Because it's decreasing at a rate of 2 centimeters per second, I'm going to put negative 2. While the width is increasing at a rate of 2 centimeters per second. So the width is changing at positive 2 centimeters per second. When L is 12 and W is 5, find the rate of change of each of these. So this means D something. Can I plug L and W into my problems once I set them up? No, because L and W are changing. They're not constant in this problem. So I have to plug them in at the end. Let's do problem A, the area. Well, I need to know a formula for area of a rectangle. If you don't know, go back to geometry. It's L, W. Now, if I'm changing, what in calculus can I do to show change? I can take the derivative. What's the derivative of A? It's dA. Be careful here. This answer is not dl dw. It's first times the derivative of the second plus the second times the derivative of the first. Now I've taken the derivative so I can plug in all the things I know. I want to know how fast the area is changing. I know that the length is 12. I know that dw is 2. I know that the width is 5. I know that the dl is negative 2. And I get an answer of 14, and the units would be centimeters per second. Centimeters squared because it's area. Okay? Pretty straightforward problem there. Let's move on to part B. The perimeter. Same setup, but I need to know the formula of perimeter is 2L plus 2W. I can't plug in anything because it's all changing. Perimeter, length, and width are all changing in this problem. So let's take a derivative. What's the derivative of 2L? Well, it's 2 dl plus 2 dw. Plug in everything you know. dp equals 2 times dl was negative 2 plus 2 times dw is 2. Hey, and look, it cancels out. Which makes sense. If the rectangle is getting smaller this way and bigger this way at the same rate, your perimeter is not changing, but your area can. A skinny rectangle has a smaller area than a more square rectangle. So perimeter isn't changing in this problem, but area is. Part C. Part C is a good problem because it does not give you all the information you need. A lot of the ones you're going to see are like this, where there's not all the information given. The length of the diagonal. What do I mean by diagonal? Well, here's a rectangle, and that's a diagonal. You can call that the length, the width. I'm going to call that the diagonal. What's the relationship there? I don't have a formula for diagonal, but if you're smart, you can see some sort of relationship to relate these three things together. And it's w squared plus L squared equals D squared. Okay? Time to take a derivative. 2w dw plus 2l dl equals, this gets really dumb, 2d d diagonal. That stands for derivative of the diagonal, so I'm going to put it in parentheses. Now let's plug in everything that I know. Well, I know that the width is 5. I know that dw is 2. I know that the length is 12. And the dl is negative 2. Uh-oh. I'm missing something. I want to solve for dd, but I'm missing a variable. I'm missing d. I need to find that before I can finish this problem. So I need to come over here and figure out what d is. Well, if I know that the width is 5 and the length is 12, I can use Pythagorean theorem to figure it out. In this case, d is 13. So I'm going to plug that back into my problem. So now I have 2 times 5 times 2 plus 2 times 12 times negative 2 equals 2 times 13 d diagonal. From here, it's just a matter of solving some algebra. I'm going to save you some steps and tell you that dd is equal to negative 13 centimeters per second. There's a problem where not all the information was given in the first explanation. You had to use what you had to find something else. Now, in these problems, everything was changing. Everything was changing. There was no constant throughout the problem. So let's take a look at one where there is a constant throughout the problem. The mechanics at Mercedes Automotive are reboring a 6-inch deep cylinder to fit a new piston. The machine they are using increases the cylinder's radius 1/1000th of an inch every 3 minutes. How rapidly is the cylinder volume increasing when the bore is 3.8 inches? Now, for those of you that don't know anything about cars, let me explain to you what's going on. There is a cylinder that's inside the engine. Okay? They are making it wider, so they're drilling it out. This cylinder is in a big block of metal. And they're using a drill. There's a drill, to drill this thing out, to make it larger. So, this cylinder is going this way. The hole is going this way. Okay? So let's stop and think about this. Well, the first thing I'm going to need to know is I'm going to need to know volume of a cylinder. And for those of you that remember it, it's pi r squared h. Now let's figure out the things that we know. Well, we know that it is 6 inches deep. In this case, depth is height, so I know that h is 6 inches. It increases the radius, so the radius is changing by 1/1000th of an inch every 3 minutes. And I want to know how much is the volume increasing, so I want to know how much the volume is increasing, I don't know, when the diameter is 3.8 inches. Well, right off the bat, you should see something. I don't care about the diameter, because diameter is not in my formula. What do I want? I want to know that the radius is 1.9. Okay? Also, before I get further, let's stop and think about this. Here's the cylinder. It's in this block of metal. This open cylinder, this hollow cylinder that's getting bigger this way. The volume is getting bigger because the cylinder is getting bigger. What isn't changing? The radius is getting bigger, but the height isn't. The height is constant. I'm not getting deeper, I'm only getting wider. So this thing right here, this height is constant. Since the height is constant, I can go ahead and plug it into my formula. So now the volume is 6 pi r squared. Now it's a much, much, much easier problem to deal with because there's only two variables. Let's take the derivative. Oh wait, let me stop again. Why could I plug the 6 in before the derivative? Because the 6, the height, was constant throughout this problem. So dv, the derivative of this is 12 pi r dr. Plug in everything you know. I don't know dv. 12, pi is pi. R is 1.9. dr is 0.001 for every 3 minutes. And to save you a little bit of time, that is exactly 0.0076 cubic inches per minute. If you want to get more technical, it's roughly 0.024 cubic inches. Sorry, 0.0076 pi cubic inches, which makes it 0.024 cubic inches per minute. I don't care whether you give me the answer with pi in it or whether you multiply it out. Either way, it's the same thing. What other type of problems could look like this? Well, imagine water draining out of a cup. The height of the water is going down, so the height is changing in the cup. But what, as the water drains out, isn't changing in the cup? The radius. There's an example of a problem where one variable stays the same. Another example that comes up that isn't like this would be sand coming off a conveyor belt and piling up, so it makes a cone. What's changing there? Both the height of the pile and the radius of the base. So be aware of what they're asking you. If you have trouble with this, come talk to me. I'll give you more practice problems. Otherwise, guys, have a great day.